Greetings, ChipX Israel. It's my pleasure to be speaking with you. I wish I could be there in person and hope to be able to travel to Israel soon. Congratulations to all of you for hosting such a promising event. A little bit on background. My name is Neeraj Paliwal. I lead a team of cryptographers and semiconductor security experts as the GM for Rambus Security IP business unit. Well, many of you know Rambus as the memory technology innovators. However, we also happen to have one of the largest team of cryptographers, over 2 decades of track record from CRI and Inside Secure. Our inventions range from silicon countermeasures for differential power analysis to being one of the top 10 algorithm finalists at NIST post-quantum cryptography competition. For the topic today, over the last 2 years, we've been hard at work looking at semiconductor security topic for custom chips, AI, ML processors. We're attacking this problem by following 2 basic principles. One, start thinking about security at the chip design architecture stage, instead of waiting till engineering samples on the first test chip or the chip. 2, while architecting for security, when we design security technology, we always assume that the chip will end up in zero trust environment. That has certain implications on how you design the security threat model. So solving semiconductor security problem becomes more complicated as these new design starts are gravitating towards custom silicon, where Google's head of Israel Semiconductors division recently mentioned that SoC is the new motherboard. And I truly believe in that. I've been in the processor side for over 2 decades, and I've seen integration in semiconductor happening over and over again, but we have never seen at the pace it's happening in last 5 years. You see that there is a separate AI processing unit like TPU, then there is a separate one that does video encoding for YouTube-like applications. So this is really the era of very highly specialized custom silicon. And that's why we want to get into, before we get into real presentation, let's just touch upon what exactly is happening in this custom silicon domain. So we see 3 main advancements that are redefining the security threat model for today's semiconductors. 1, heterogeneous compute. So new workloads in AI, ML are driving the privacy needs. Centralized, decentralized infrastructure by 5G is driving the approach towards where security becomes increasingly more important when your device is not inside a data center, but actually is an edge device enabled by high throughput data in communication with 5G. The third advancement we see in technology that makes security complex is the new technology around packaging and advent of chiplets, because then you are truly functioning in a zero trust environment, because earlier you used to know inside your die what is the circuit that's inside. Now when you integrate these chiplets, the security threat model becomes even larger and more complex. So in this presentation today, I'll talk about securing the data center AI ML workloads and assets. The session is divided into 3 parts. The what part, where what problem are we solving? The how part, how we solve the problem. And I concluded with a use case around the problem on AI ML security. If you look at what's happening at the AI ML chip level, the data centers handle large amount of AI ML training workloads for their independent customers. And the vast number of these workloads call for very efficient processing, where you are designing this highly specific MAC block to do matrix multiplication, and you're optimizing memory to be co-located or be close to it to be able to access the memory. And to handle these workloads, dedicated AI processing hardware is appearing on the market. These new architectures are offered as pluggable blades, And they implement the latest state-of-art neural processing architectures. Many new startups in the marketplace are starting development and offering such implementations on custom silicon. And the actual workload that is to be handled, whether it's inference models, inference algorithms, training models, and training data sets, they're all considered valuable intellectual property. They need protection when they are out in the field, especially on the edge device. So when these valuable assets on the AI accelerators are handed off to data center for processing on shared hardware resources, security and privacy of the data becomes even more important. So that's the problem landscape. So how can a supplier of AI ML acceleration services ensure protection of their customer assets? So like in every segment where security become important, a secure by design approach need to be followed. Security implementation cannot be an afterthought. What I mean by that is when I'm designing the architecture for the chip, at that time, defining very clearly how the data will flow from cloud to that device, how it will be authenticated, when it will be flushed out of the memory. All those things need to be thought through, and that's what we call secure by design. And various aspects of security need to be taken into account in the planning and architecture phase itself. Good news is, security and cryptographic solutions do exist today that can handle the high throughput requirements of this AI ML segment. If you look at, let's dig a little bit deeper on what itself the problem. What are the AI assets at risk? To start with, let's refresh the memory about what these assets are. There are mainly three product families. If you look on the top of this diagram: data center, edge node, and endpoints. And there are many threats, whether it's malicious or intent to steal valuable assets, attacks that can occur at multiple layers, software, firmware, hardware attacks. They could be invasive attacks or non-invasive attacks in some cases, man in the middle, or across the network from the core to the edge or at the endpoints. That is the kind of environment these chips are functioning. So it will be critical to safeguard the data that's handled in the AI ecosystem. AI-powered devices are flying our skies. They're driving our roads. They're protecting our neighborhoods. And an attack on these accelerators, AI accelerators, can compromise the data that's going from one to the other place on this ecosystem as described on the diagram. To protect these assets at risk, the various threats like denial of use, misuse, device and data tampering, asset theft, or many other need to be handled appropriately. So in the next one, we look at what are the components. When we talk about, so far we have explained the problem space. When we try to solve it, let's first look at what's on the block diagram of this chip we are trying to make secure that we call AI ML accelerator. The heart of the system is obviously, like I mentioned earlier, it's an array of powerful accelerator chips, or in some cases, these MAC blocks in highly parallelized shape placed one next to each other. They're ranging from a handful to a large matrix of dedicated AI processing units. They have their own pool of memory, and they have only one task. And that task is process as many AI ML workloads on as much data as possible in the shortest time frame with the shortest latency. So when I am a startup trying to optimize that problem, trying to figure out the ML framework, the software, the hardware, the AI accelerator, security we notice in these startups and in many of the custom silicon chips is quickly overlooked until the engineering sample. And then it's also looked at as an overhead on your latency. So not always present, but typically seen on these blades is a gateway CPU. It has its own dedicated flash and DDR. And with the task to manage these models and assets, to control the accelerators. Finally, there's going to be a connection to the fabric as you look at the block diagram of this accelerator. There's going to be a connection to the fabric, being a high-speed network or PCIe 4.5. In some blades do have proprietary interblade link also. So we have now looked at what exactly is it that these blocks are made up of. If we go to the next one, it talks about, like in any system these days, AI accelerators need to follow security requirements at a minimum. And what that minimum means, even if you look at a chip from 5 years ago or a secure microcontroller, they need to be able to authenticate and protect the blade itself. So for authentication, a blade would get an ID, an identification number, like when a baby is born, we give a baby naming ceremony. In a similar way, the chip needs to be given an immutable identification that you can validate and authenticate. And it not necessarily need to be kept secret, like in humans. It just needs to be unique and immutable. This ID is typically injected in a personalization phase in the chip, right at the back-end manufacturing, sometimes burned on the ROM. It can be in final assembly or test, as for example. Note that there can be many IDs, one for each chip, one for the blade or the appliance itself. During the life cycle, there could be different IDs or multiple identities being used by the OEM or the chip maker, or by the data center owner, or by even the consumers or the B2B final user of that AI workload processing. Provisioning and key management is done in the later phases. During the enrollment, for example, in provisioning, the services, the key materials and certificate for such services are defined and loaded into a system. So far I'm explaining a traditional security requirement of most of the chips that come across. Protecting these blades itself is all about trusting the appliance, which builds upon the previously mentioned device ID, as I mentioned, provisioned keys and certificates that you can manage through lifecycle. And using these assets, a trusted or secure boot chain can be established from the anchor down to the chip, the root of trust, all the way up to the applications that's being used. Using these assets, a boot chain can be established where a master CPU, this could again be a gateway CPU, validates the software image for integrity and authenticity of the chip, using strong digital signature schemes before allowing the system to boot. So this is all still being done in a traditional environment. And software confidentiality is something which is important to protect the intellectual property, can be guaranteed by using image decryption techniques. So all these protections can be managed by the gateway CPU, for example, or by the accelerator units itself, or they can be managed by both in tandem. Let's now get into a little bit on how you expand these security requirements specifically for the AI ML accelerators. So elevating the security requirement for protecting the blade, it requires one more level. For example, tamper detection and memory protection, where earlier traditional requirement would handle the static assets such as firmware and keys. The new requirements on AI ML accelerator ensure that the blade can keep functioning in a trusted manner after it's deployed. There are mechanisms to detect tampering, like bus probing, clock and voltage glitching. It may protect against bypassing the secure boot process. The most elaborate secure boot scheme becomes void if an attacker is able to glitch the final go and no-go decision gate in secure boot process. So that's why we truly believe secure by design early in the architecture phase, and implementing security in hardware is a must, because one failure can actually create huge implications on the privacy, security, or even the functioning of that accelerator in the ecosystem it's playing. In addition, the ability to service the blades in the field in a secure way is very, very valuable. Secure firmware updates, as well as ability to be able to debug the system in a secure way, these are becoming almost like table stakes as we look at these things. Now, if you look at the further requirements for the AI/ML accelerators, where the previous slides discussed protecting the equipment itself, there are specific security requirements in the acceleration as well. One of them is protecting the assets. And by assets, I mean the models and the weights that might be highly proprietary for a cloud player, because it actually is their secret sauce. So secure AI implementations are required to prevent the extraction or stealing of the inference algorithms, models, and the parameters, training algorithms. So now you see, until now, we are unpacking this layer on the onions. First, we talk about traditional security requirement. Then we talk about the data center environment. Now we're talking about the AI accelerator related security requirements. This would also mean that the prevention of unintended replacement of these assets with malicious algorithm or data set is also required. Protection against this would avoid poisoning the system to alter the inference results, causing a very famously in AI, we call it misqualification. And you have seen these pictures or these highly sensational news that you inject a little noise in an image, and suddenly the AI detects it from detecting it a picture of Mona Lisa to a dog or something else. So also important are the data privacy regulations, because many of these AI accelerators end up in healthcare or in Europe, where HIPAA in the healthcare and GDPR in Europe are not violated by the equipment. So how do you take care of the security to meet the regulations? So when these AI blades are installed in public cloud servers, they tend to be assigned to handling workloads of various tenants dynamically. Ability to switch between different users or tenants in a secure way avoids the contamination, and it protects the assets. Finally, on the requirement side, security should also be present to avoid misusing the system, to ensure proper billing of services, commercialization, and to prevent unethical use of such as racial profiling and many other societal issues that we see. If we move forward, so we have now very well defined the threat, the problem, as well as the requirements in this particular AI/ML case. Now let's look at whether the data is at rest or in motion. How do we protect the data? To meet the fundamental security requirement, we need to ensure data is secured while it's resting, as well as when it's in motion, in between devices. There are methodologies such as simple encryption using cryptography that are fundamental to protecting the data at rest and in motion with high-speed encryption cores. Underlying algorithms for both of these are typically the same. They're built on well-established and crypto-analyzed cipher and hash algorithms. The difference is, for data in motion, the throughput requirements are extremely high because data is moving, very low latency requirements, and the used key materials are ephemeral, as they typically work with short-lived session keys that you see starting from any requirement you see, whether it's MACsec, IPsec, TLS, any of these protocols. On the other hand, the data at rest, typically, it will allow adversaries to have more time to analyze and attack such systems, because assets are often static and stored on devices, in some cases, highly valuable, like keys or immutable identity. And that's why you see more protection mechanisms such as secure provisioning, anti-tampering, side channel protection in the data at rest column here. Now let's get into one of the two principles we work with, architecting for security. As we look into complete architecture for AI security, Beyond the accelerator only, we have to implement with the security by design principles. So we have covered a lot of ground so far. Let's get into what we see here. Again, is the typical AI blade or appliance block diagram with the gateway CPU, the accelerators, the DDR or GDDR module on the right, communication link being PCIe or some high-speed network. Let's inject the data in motion security module mentioned in the previous slide. The network or PCI link to this fabric should be protected by inserting a high throughput L2, layer 2 or layer 3 protocol aware security packet engines. Such a packet engine has secure protocol awareness and requires little support from the CPU, thereby the basic concept of the security siloed execution being enabled here. Moving on, data at rest protection on the AI blades. As stated earlier, data at rest protects assets such as keys in OTP, firmware, device identity, and device settings. The vital component in protecting the device and the data at rest is the hardware root of trust. And a hardware root of trust can be a discrete component on a blade. Typical examples are TPMs and secure elements and the chips. It could be integrated in the baseboard management controller, but this is not common. Higher level of security integration for data at rest protection can be achieved by embedding a root of trust, as I'm showing here, into the CPU and the NPU itself. So far we have covered two components, the what component and the how component. Now let's get into some use cases as the last part of this presentation. Because what good is a theory if I don't share with you how it's implemented and how the data flows? Let's look at a couple of use cases. One of the major use case is ensuring the availability of the AI accelerator from adversary. Adversary can tamper with accelerator hardware to deny or disrupt usage or bypass its security measures. The root of trust core embedded in various ASICs, it can independent of application, CPU or NPU, it can monitor system status and memory contents, and it can detect tampering activity. So in summary, we have presented that dedicated new neural processing architectures appear on data center blades, where higher value of inference model and training data and increased network vulnerabilities increase the risk and need for security. Deployment of well-architected multi-layer security will protect the data at rest and data in motion, where securely anchored root of trust hardware provides the highest level of protection. This hardware root of trust and security protocol accelerator embedded in an AI accelerator and edge device will protect the physical hardware, inference model, training data, and inference results from a broad range of threats. I want to thank you. And if you would like more information on the security solutions as discussed today, please visit us at rambus.com/security. Thank you very much.